You're listening to Within Tolerance Podcast, a podcast for machinists by a machinist. I'm your host, Dylan Jackson, and this week I am joined by Marv. Marv, take it away. Who are you? Where can they find you online so they can pull you up on Instagram or whatever and follow along as we dive into your backstory?
Hi, I'm Marv. Normally called Marvin Groeb, but that's kind of hard for all Americans, so Marv is totally fine with me. You can find me on Instagram with the @MarvGroeb tag, and I'm on LinkedIn. I also have a YouTube channel, but that one is in German, so probably not interesting to most of you listeners.
I mean, the things you're machining in there are definitely interesting. I've watched
Oh
a
yes,
few of them.
the machining videos are interesting. You're correct.
Well, very cool. So let's dive into it. How did you get into manufacturing? You're also a scientist background, which was what really drove me to take your class at AU, which is the first time we met. But how did you get into all of this?
I think it was mostly by accident. After school, I thought about what I could study, and I actually applied for mechanical engineering and they didn't take me. In Germany, the study system works by having a so-called numerus clausus, which is Latin for like a number restriction on popular study courses. And the year I finished school, Germany changed their schooling system that you finish it 1 year earlier. So it was twice the applicants, and I didn't get into mechanical engineering. And then I looked around, and the University of Darmstadt, where I studied, has a course on material science. And this has actually pretty much nothing to do with knowing about materials, which is quite fun in my normal work. But it's mostly about solid state physics. And I was really interested, and I still think this was probably the best decision I could have ever made because it was just so hands-on, and I learned pretty much about every analytics technique there is during my studies. So that was really cool. And how I got into manufacturing, I used to go to the local makerspace in Darmstadt. And one evening, the head of development of Datron, they produce high-speed milling machines, he came by and he basically said, they are looking for people who can do quick and dirty. And I thought, this is my calling. I have to apply there. Yeah, I think you can say the rest afterwards is history. They gave me my first CNC introduction, which was like 2 days on how to operate the Datron. And then they showed me an empty building with like 2 CNC machines in it. And they were like, yeah, can you machine a wooden box for our, I think it was the sales manager, like a CrossFit step box? And they just left. And they were like, here are tools. You know how to put tools into the machine. There's a computer. There's Fusion on it. And here's the wood. Just make a box. And they came back 2 hours later. I think they expected me to cry. And the box was finished. And
Wow.
I was hooked. I was just like, okay, CNC is the coolest thing ever.
That's awesome. So what did you do? I mean, after the box, what were you doing at Datron?
I was mostly testing. So Datron, they actually, I wouldn't say they run on, but their application department has tons of students working there. And it's actually really great for the students because they get to pick up skills they otherwise wouldn't have. So it's a big plus, actually, and not like students running wild there. And they had me testing. It was both testing software, testing new tools. So it was a little bit a step between tool development and testing the beta releases. And after about half a year, they discovered that I spent pretty much every evening and every weekend just milling there and milling stuff for my personal workshop or for my home, just like milling everything. And then they asked me whether I wanted to start doing social media marketing for them, just like mill something. And while you're milling, test tools and test machines and software, but mill whatever you want. And from that point on, it got really crazy. I think in my 2 years at Datron, I've spent every weekend there, often milling late into the night, sometimes running 6 or 7 machines. It was really fun. I learned a lot. And the great thing was they were so relaxed about everything. You could just get the key to the application department and go mill there on Saturday as long as you took another colleague with you so you weren't alone.
Wow. That's pretty amazing. I mean, that sounds like many of my listeners and myself kind of a dream job to have right there.
Yeah, and don't forget Datron is a tool producer, so for them the tools are affordable. So not only have you unlimited access to industrial milling machines, but also a fully stocked drawer with every tool you'd ever imagine. And if there is one you want, you can just order it from their main headquarters.
Oh my
So
goodness.
yeah, it was seriously the dream. And I've actually kept great contact with them. Obviously, not for the last 1.5 years, but even while I was working at Kern, I was still always welcome there and actually spent a couple of weekends still milling there with some friends just for old time's sake.
Oh, very cool. So you mentioned it. Now you work at Kern. How did that?
Yeah, for me, I've spent during studying a year in the actually French Alps. And let me tell you, studying solid state physics in French language when it's not your mother tongue was the absolute horror. But living in the Alps was fantastic. So I always decided for myself when I finish my studies, I have to move to the mountains. And well, that's enter Kern. They are directly next to the German Alps. I now live like in direct view of the biggest peak of Germany, but also they kind of like had a more permanent position for me. So my business card says I'm a systems engineer, and I think no one, including myself, has any idea what that actually is. I'm a researcher. So what Kern expects of me is, you could say, drink coffee and know a great many things, to pull out an internet meme. I do research into milling, and I'm also an expert at Kern for certain applications, such as hard milling or surface finishing. And my work is kind of split between doing really basic research, understanding how chip formation is happening and how to improve a process, but also, of course, helping our sales managers to convince a customer that the Kern is like the perfect fit and show them technical reasons or even demonstrations on why the Kern is a good fit.
That sounds amazing. Like quite the job.
It's challenging. I like it, and also it has no hard deadlines. I like that a lot as well. So for me, it's not like you have to finish this machine by tomorrow, or the customer is coming to see your progress on this project. But for me, it's just like, well, this year you're probably going to do a lot of hard milling, so organize yourself, and then it just goes.
So you now have your master's in material science, right?
Exactly. I actually did my master thesis at Kern. The subject was cloth finishing of hardened stainless steels. So I did like a process analysis on this one.
Wow.
And it's sadly in German, so I can't share. Kept under lock as well for another 3 years, I think. But they had a working process on mirror finishing stainless steel, with which they achieved about 20 nanometers RA, so zero point zero 0.02 micron RA.
Oh
And
my
they had a
goodness.
couple of small surface defects on that. And it's kind of funny. The first time they showed me the part coming from Datron, I looked at the part and it was like, I don't see the surface defects. I just looked at it and I was like, this is a perfect mirror. Nowadays, when I look back at that part, I'm like, oh my God, we were so bad. But back then, I didn't have the eye for such details. And it kind of started with me getting a machine introduction, then getting told I'm like the only academic who is even allowed to touch the machine. So that's kind of like nice. And then just doing trials and trying to understand what is changing the properties of the surface. And the breakthrough there was stepping away from just trying different parameters. So not just trying, okay, let's try another spindle speed, another feed rate, another step over. But this real step was when I took my first samples to back to university and looked at them in a scanning electron microscope, a really nice one actually. And you could see at the edges of the small parameter fields I trialed, you could see how the chip formation was happening. And we then realized we are not cutting the material, but burnishing it. And that changed everything completely. And nowadays we can achieve single digit nanometer roughness there. I'm not comfortable stating numbers below 10 nanometers because then our salespeople listen to this and sell machines, and I have to really tune processes. But we can go below 10 nanometers now, and the surface defects have disappeared. So that was like a really cool intro into milling at Kern.
So that actually brings up, it was kind of where I was heading with my question was, because you've started your manufacturing career from the scientist perspective, how do you develop speeds and feeds? And that'll kind of dive into some of our other listener questions as well, as far as surface finish. But like, how do you, when you're cutting a new material or a new process, or new tooling or whatever, what is your process for developing speeds and feeds rather than just trying the gamut and hoping for the best?
Yeah, I think one of the biggest issues with trying out feeds and speeds is that it's an engineering approach. So the difference is if you have a scientist, and for example, that scientist is doing his PhD, they have all the time in the world. Well, at the end, not, but at the beginning, they have all the time in the world and they want to really understand what is happening. So they start designing experiments that will, for example, provoke errors because they have that time. And if you look at an engineer, well, at the end of the day, someone wants a product which you can still pay for. So mostly feeds and speed variation is about not understanding the underlying principles, but also it's about quickly reaching your end goal. So for that reason, what engineers do, and I mean this works in a lot of fields, and up to a certain point, they vary a lot of parameters at the same time. So maybe they change the spindle speed, and then they also change the feed rate or the depth of cut to arrive there. And there are some mathematical methods where you can later distinguish between these. A scientist, he would start at spindle RPM 1 and then try RPM 2 and then go through the whole range until he arrives at max spindle RPM. And then he would change the depth of cut and try all of these again. Now, obviously, me working in industry, we don't really have the time for that. I can't, as much as I would love to go through it, the amount of material, tools, and time, no one could pay for this. But I think my method differs from what a usual engineer would do in being more methodic. So I don't just start by variating feeds and speeds, but I look at what am I cutting. And for example, if I'm cutting aluminum, it's a soft metal and it's actually the perfect example of high-speed milling. And with aluminum, it's always more cutting speed is always better if you have a stable machine. So on a Kern, it's always don't use 10,000 RPM, use 30,000 RPM. And if you have been using 30,000 RPM, use 40,000 RPM, and everything will improve. So for me, I look what does the material like, and for this I have a bit of a database and lots of experience and scientific papers that show what is like the main factor for the material. And then I do experiments on changing the rest of the parameters. And I don't really just change feeds and speeds, but I try to make it in a methodic way. So before I start, I sit down with a pen and a piece of paper and I think like, at what parameters do I want to look and what will they show me? So giving you another aluminum example, if you do free-form surface finishing in aluminum, your kinematic roughness has a huge impact. Because the tools are so good nowadays, it's actually, you can easily, on a high quality machine, approach the kinematic roughness, which is the cusp height between your individual step overs. So this is something to keep in mind. And I've seen lots of actually really great tool makers wandering and trying different feed rates and different spindle speeds. And all the time they were just at their kinematic roughness limit. So this is something like plan out your experiment series before and look at what you really want, what you're really changing with a parameter, and then go for it. And afterwards, look at the results. And I mostly like for my basic research, I use Excel. And then I just like highlight parameter sets that were really good, where I had a good surface roughness or good precision. And then I try to kind of abstract knowledge that will help me in every situation and not that part.
Okay, that totally makes sense. And it sounds like you truly just abide by the scientific method. Like you come up with a hypothesis, you test these hypotheses, you record all your data, and then go from there, which is refreshingly different than I think what a lot of purely machinists do. It's kind of cool to hear.
It's definitely a more sciencey approach. I mean, my colleagues from studying, they always shake their head when they see my experiment series and they're like, you're not looking at everything. And I'm like, yes, but I have to earn money as well. So,
Yeah. Well, and I think that, like you said, that's why a lot of engineers and machinists don't go down that approach, is because they don't have even the time to test six things. It's like I've got time to test maybe two, possibly a third if they both fail, and then I've got to make parts. So
I'm fully with you there, but sometimes taking those extra 30 minutes will save you a lot of headaches. Because if your process is just good enough for the part, what happens when your tool wears or when your coolant nozzle gets pushed to the side? And if you have a process that is much more stable, I mean, all your parts will probably be good. So it always depends. If you're rushing a part or if you just need to finish a part, okay, what works works. But sometimes just taking that half hour more will save you so much headache along the way.
Oh, totally. I agree. I was actually just lamenting the loss or lack of cam challenges last night on the Discord, and the one reason that I really enjoyed those was for that freedom to kind of experiment. It was like I could play around with design, I could play around with different strategies, different stepovers, all that stuff, and not have the worry of like, oh, my customer is waiting. It was like, well, if I don't get it done, I don't get to post it on social media. No big deal. So yeah, it's nice having those freedoms for sure.
Oh yes, the cum challenges always were awesome. Great fun.
Yeah. So you had mentioned cutting aluminum. I don't know, what was it? A few months ago, posted all kinds of pictures and videos of this insanely surfaced cube. So is that when you were finding out about these kinematic limits of surfacing
Well,
aluminum?
that cube actually has a backstory. Our CEO is probably gonna hurt me on Monday if I tell it, but that's all fine. So I was invited to speak at a seminar for ultra precision machining, which is curious because we are not an ultra precision machine tool builder. We are a high precision machine tool builder. And something I wouldn't call it I had developed, but I think no one has thought about this for a very long time, is scribing with a CNC machine. So you probably know all those really old, I think they are called shapers, where
Mm-hmm.
you have like a turning tool and it moves linear through the material. Those kind of like, at least in Europe, fell out of favor once high-speed steel was discovered, and then milling was more productive than shaping. And with carbide, it changed even more. And back then, the machines were too maybe rough to use diamonds to shape something because diamonds don't like large impacts. And in the spring 2 years ago, I thought about like it would be so much quicker if we just stop turning the spindle. And I think this is something half of Instagram still hasn't realized, even to Stefan Gotteswinter was the first to comment that the spindle is not turning. This cube was made without turning the spindle.
Really?
So what I did is I took a diamond tool and then I looked at the analog output of our tool setting laser and adjusted the tool so it was totally parallel to the laser axis, so finding the orientation of the tool. And then on the Heidenhain, you can accentuate the spindle in any position you want, for example, for probing. So I used like that cycle on the Heidenhain. And then I hand programmed parts of that cube, and the tool is actually just dragging along. So it's really like 5-axis shaping.
Wow.
And one of the advantages of this is that it's so much quicker. Because usually when you're diamond milling with monocrystalline diamond tools, you are limited by your feet per tooth. I already mentioned diamond doesn't really like hard hits on it. So if you take more than 10 microns per tooth, your diamond tool will not like this. So at 30,000 RPM, this comes down to moving at 300 millimeters per minute. That's, I think, 12 inches per minute. So not really quick to diamond finish. At the same time, you have a very small step over, and you're totally correct. The kinematic limit quickly applies there. If you stop turning the spindle, you can move however quick you want. So you can, for example, move at 10 meters compared to 0.3 meters per minute, which is how I finished that cube. And the fun part about that story is my original demo piece, showpiece, was just like a head-up display mold. So a small piece of aluminum, flat, just a single curved shape on it. And once they finalized all the speakers for that UPM seminar, I saw that Fanuc is going to be there and presenting their Robo Nano, which is like a super precise Fanuc machine.
Right.
And it's made for making head-up displays. okay, there's no way I can compete with this. So I thought about what can I do? I had like 2 days left, like the weekend and the Monday left. What can I do that Fanuc can't do with their machine? Because obviously I don't want them to show me up. And one huge issue for UPM machines is the weight of the workpiece. Because they use air-bearing spindles for the workpiece, you can't really put a lot of weight on these, otherwise they get unstable. So I just took the largest piece of metal we had lying around and decided to do a shiny spark, as we call it, over the weekend. It was fun.
That's insane. That is really cool. Yeah, because I've looked at the Robo Nano a few times because all that is pretty much like a nanometer controlled shaper, kind of.
Yes, exactly.
So
And
it's very interesting that you were, not really going up against that, but sort of going up against that and had to show them up, and I appreciate that.
yeah, I think it comes down to, with the Kern machines, it comes down to that productivity. So obviously, the surfaces from the Robo Nano are much better. But at the same time, that machine has no spindle power. So what was interesting, and I think Fanuc was, I would say, not amused by me, that I put focus on the way we were roughing out that part. Because what the UPM guys always tell you is, you're like, yeah, you just buy like a Hermle or a Kern and put that next to your UPM machine. But then you have two very expensive German machines sitting there, and you have to synchronize them, and one will always be standing around waiting for the other. And on the Kern, I mean, I was roughing that cube with 15,000 watts of spindle power. That's like 20 horsepower, I think.
Wow.
And 1 minute later, I put in the diamond tool, started the finishing pass, and went home, and you don't see anything. And that is what kind of makes a Kern machine special.
That's amazing. So I don't know much about Heidenhain controls. Is that now something? Because you said you hand programmed some of it. Is that something that you can create a custom cycle for in the future if you?
We are at the moment developing that tool orientation cycle because the first of our customers are interested in that. So we first have a very good connection to Heidenhain. For them, we are kind of like the experimental lab. Our problems are the problems their regular customers, who actually earn them a lot of money, will encounter in 5 to 10 years, because even normal machines are approaching what current machines used to be 20 years ago in precision. And we have a very good relation to them and can change a lot on the control. But also, we are a machine tool builder, so on a PLC level, we are able to program quite a few of cycles there. But that program that I did was just like basically a loop program going through circular passes to create those shapes. So the outsides of that cube are just like really large globe segments.
Right. Yeah, that makes sense. That's cool. It's nice that you have such a close working relationship with them.
Yeah, one of the other reasons I hand programmed it is because I did the upper surface of the cube in CAM because I thought it would be quicker. And I mean, this is not really a drawback of a current machine, but that machine does exactly what you tell it to, not more nor less. And if you have freeform surfaces and you diamond finish them, you see everything. And every CAM system, besides Tebis, I think, is working on a mesh. So when you hit calculate, what it does is convert your step file to a mesh file, like an STL file, and
Right.
then it's calculating on that one. And if you use, like, for example, Fusion standard settings on a kern, you will see the mesh. You will see the individual points of the mesh. So it's not the points of your toolpath, but you will see where the toolpath goes around the mesh. And that is like an absolute horror to get rid of, because you kind of need to like increase the mesh tolerance so much that the mesh is so fine that you don't see it anymore. And on that part, that scribing process, that's how I call it, is so precise that you can actually see everything generated by CAM. And the top surface, which is why on Instagram you mostly see the sides of this cube, is actually not completely clean, because there you have a couple of CAM artifacts.
Well, I would imagine you have to increase the tolerance or decrease the tolerance so much that calculation times probably go through the roof.
Exactly. That as well, yes.
So, speaking of surface finish, a few of the questions we had from listeners, Design the Everything AJ asked, "What are the best methods for increasing surface finish quality on cheapo machines. He's got a Tormach and I think a Pocket NC as well. But you've now had, experience on Kerns and also Datrons and things in between. So what are some generic ways to increase surface finish?
I think the first thing to look at is the tool and how you are holding the tool. So the tool holder. With the tool, in general, in every material except titanium, your surface finish is depending on how sharp and how well made is your tool. So a very easy solution is to just buy a better tool. And I know this is really expensive sometimes. But even in the process, you have a couple of choices. So I already told you on soft metals, so aluminum, brass, copper, cutting speed equals quality. So you can just increase the cutting speed. Then the next thing I do when people on Instagram ask me for a bit of help is to look at the setup. So what kind of tool holder are you using? Because even if you're taking a finishing pass, the deflection is actually massive on the tool. Massive in terms of you're trying to create something along the wavelength of light. You always have deflection in that range. So I would use the best tool holder you have in terms of runout, which is very important if you have more than one cutting edge. If you have one, it doesn't really matter. And stiffness, but also dampening. So shrink holders, like heat shrink holders, are a really good solution for high quality finishing. The last thing to look at is how are you fixturing your part? Because if your part is, for example, glued down, it is something I do from time to time as well. But that's not the best possible solution. So try to make everything as stiff as possible. If your machine is not very stiff, so I think, for example, on a Pocket NC, start your machining pass way outside of the part. I usually, in Fusion, for example, I use just like the Surf workspace, and they actually pushed an update where you can now do like easy tangential extensions of surfaces a couple of months back. And that is something I use quite a lot when using Fusion to finish parts, that I just extend the surface a little bit outside the part. And then when your machine starts, because it's probably moving at rapid feed rate around the part for the next pass, and then it kind of needs a small amount of time to stop swinging. And that will decrease a lot of your ringing marks or anything that looks like dynamic errors. In general, I think even on a cheapo machine, you can get good quality finish, just be methodic about it. So start like an Excel sheet and start recording what works for you and what doesn't work for you. And then try to make your cheapo machine as good as the big ones. So make it stiff, make it stable, try to get a lot of RPMs into it. And then you should actually go pretty far.
Awesome. And then another question about surface finish, wannabe machinist asked, what parameters are you optimizing when you're trying to get the best surfaces? So once you have that Excel document, what should they start varying and how methodical can they be? I mean, you talked about creating a hypothesis and varying everything very incrementally, but I guess, for somebody at home who might get frustrated easily, what can they start? What do you find is the easiest way to get to a best surface finish?
Well, the easiest way would be buy a Kern. I mean, what are we talking about? When you're sitting at home, I think sometimes you arrive at a point. So in the beginning, most of the parameters already told you are a good start. You can go for cutting speed, you can look at the step over, you can look at the cutting depth. And those three are the main influence. So it's always better until your tool is rubbing to decrease the depth of cut and to decrease the step over. So just like making everything a little bit finer will probably lend you a better surface. For example, if you are facing on a cheap machine, it's not a good idea to just like face with a large end mill and then have a huge step over. Your machine is not stiff enough. But if you, for example, want a super even surface, even on a cheap machine, take a ball end mill. It will take ages, but your finish will be super regular because you don't have any ringing. And that is because the cut is so much smaller than it is on the large end mill. So that is something you can get quickly to a point. So just like changing those three parameters. But at some point at home, you will get stuck. You will want to increase your surface finish and it won't go forward. And then you kind of have to be the scientist. And something very cool which lends results almost immediately is to program it in a bad way. So let's say the issue with your part is your cooling. You have an air blast going on, and the air blast is making the tool ring. Okay, try machining it without air blast, just a small little bit, and look at the surface and look at what is changing. And if you, for example, turn off the air blast, and then you have no more ringing on the part, well, obviously your air blast is in some way getting the tool to oscillate. And that is something that immediately returns something. Or, for example, go from climb to conventional milling, and you will see whether you are on the right track.
Huh. That's a really interesting way to put it. So, jumping back to your degrees and being a scientist, David Ron from the Patreon asked, what drew you to your degrees? So, you said you didn't get into mechanical engineering. Was there anything that drew you to material sciences, or was it just you wanted to be in engineering and this was what was open?
I think you put a really good point already in it. It was something I could get into at that year. And I actually considered, well, if it doesn't work out the next year, I can easily switch back to mechanical engineering. But this was not my only choice. I could have also chosen just like normal physics, chemistry. I could have gone into accounting. All these were open to me. The only other thing I actually considered was studying English. And well, I kind of wanted a job that pays the bills. So English was out. And what I liked about material science is that it's kind of like the key technology for this century. So if you look back at the 20th century, the key technology obviously was IT. Computers changed everything. And now we have computers for quite some time. And what is changing the way you're interacting nowadays? And if you just look at your phone, everybody has a smartphone nowadays, I guess. And the screen of your smartphone is actually a marvel of engineering. It is glass, but it's chemically hardened glass. And what happened is a material scientist sat down and he decided, let's try doping the glass like you do with semiconductors. So putting in atoms that don't really belong there or molecules. And these atoms cause a lot of stress in the material, and that is the reason why it's so hard and doesn't scratch easily. And at the same time, why it breaks so easy. Because once you get it to break, it's very brittle. And this is what they told us at like a webinar about that course of study. And I thought like this is really cool. I want to engineer the materials of tomorrow. Once I discovered it's all math and boring as hell, flinging chips on a milling machine sounded much nicer.
So, speaking of the materials of tomorrow, you just finished an amazing watch case out of ceramic for the Hackos. Both Adam the machinist and Laney's machine tech, asked about ductile cutting of ceramics.
Oh boy, you're asking about forbidden knowledge, really. Okay, so first off, ceramics are awesome. They are what I'm talking about when I say material science is what will change this century. To give you a bit of background why we think ceramics are so cool, one of the main issues with our machine is thermal stability. So we kind of decided we want a lot of spindle power, and a lot of spindle power is like putting a heater into the middle of your machine. That's exactly where you don't want it. So what we do is we cool the spindle, and then we cool the z-axis around it, and we cool everything, and then we slap digital compensation on it. At the same time, if we switched our z-axis material from aluminum, which is very nice for keeping a stable temperature because it has such nice heat conductivity, to silicon carbide, which is a technical ceramics, we could stop cooling the z-axis. Because not only is the heat conductivity of silicon carbide so nice, it also has a much lower thermal expansion coefficient, so we could just save on cooling the axis, and that would be really cool. So ceramics are one of the engineering materials that will bring us forward in fusion energy research, but also in all applications. I mean, you even get now phones which are made from ceramics, the backside, because it's so crack resistant. One of the biggest issues with technical ceramics are they are not that expensive to manufacture, but to finish them in a mechanical way, So the powder costs like nearly nothing, and burning or sintering the powder is also very cheap. But then you are left with like at most half finished part. You kind of need to get the precision. And because those materials are so hard, so for example, the watch case I made is sintered zirconia, a dental grade one, and it has a hardness of 1400 HV, hardness Vickers. Normal carbide, which you have in a cutting tool, has a hardness of 1000 to 1200. So obviously a carbide tool doesn't work. A CBN tool has a hardness of 4000 HV, and there is a rule of thumb that says your tool needs to be at least 3 times harder than the material you are cutting. So CBN is out as well. What you're left with are diamond tools, which are in the range of 10,000 HV. It's the hardest material we know. And diamonds still fail. So if you take a diamond grinding bit to SiC, silicon carbide, or to zirconia, you can grind it for like an hour, 2 hours, maybe 5 hours. And after 5 hours, your diamonds will actually be ground flat. So the material is wearing down the diamond. For
Oh my
me, that was
goodness.
like mind blowing. I don't know if you're up to it, Dylan, but I can give you a picture of worn down diamonds if you want from our scanning electron microscope, and you can put it on the Within Tolerance Instagram so people can see it. It's crazy.
I'd love that. Yeah, I'll definitely include it in the post it alongside with the episode.
And there, quite some time ago, people, I think it was in the early 70s, people discovered, and please don't laugh at me, while cutting rock salt, that it is kind of moving in a weird way. That is how everything started. So usually those hard materials, they are brittle. Brittle means you can't deform them. And some guy in the 70s decided he wants to cut rock salt, and by accident, he discovered a way to change the behavior to a ductile behavior. Now, ductility, and I'm sorry, I'm going totally off on a lecturing mode here. You have to stop me, Dylan, if it gets too boring, okay?
I'm into it. So
Okay,
keep going.
so ductility is the behavior of a material to be deformed in a plastic way. So, for example, you can take a piece of aluminum and you can bend it. That is plasticity, and ductile behavior is like a similar word to it. And obviously, you can't take a huge chunk of salt and bend it, it will just break. So, what is happening is something a guy from Vienna discovered in 1956. It's called the Herzfeld effect. And you are basically putting so much hydrostatic pressure on the material that the atoms move a little bit closer. It's been calculated to be about 7%, which doesn't sound a lot, but believe me, it's a lot for atoms to move closer. And what happens then is that the atomic orbitals, so you have like your atom, and the atom is like, imagine a raspberry made out of, or a strawberry made out of neutrons and protons, which are element particles. And then you have electrons flying around this on like loops. And if you go one step further to how physics believes our matter is built up, those electrons are actually not just flying around it, but they can be at certain points. So it's more like a distribution of chance. So they could be anywhere. And those distributions, you can describe them in a mathematical way, they make orbitals. They kind of look like little tear shapes. And usually what defines a material, whether it's a semiconductor or not conducting, or whether it's a metal and conducting, is whether these orbitals overlap or not. If they overlap, it's a metal. And if they don't overlap, it's either a semiconductor if they are very close, or it's an insulator when they are very far apart. Most ceramics are insulators because their orbitals are very far apart. And with this Hertzfeld effect, what is happening is you're pushing the atoms so close that the orbitals overlap. And for a very short moment, this material kind of becomes a metal. And one of the key properties of metal is you have what is called mobility of dislocations. A dislocation is basically a spot in your material where it's missing an atom.
Mm-hmm.
So there should be an atom there, but for some reason there isn't one. And those dislocations, they can actually move, and they move by an atom next to them jumping over to their place. And then that dislocation has moved. And the movement of dislocations is actually the reason why you can deform metal. So ductile machining of any brittle material is actually changing it to a metal for a very short moment. And once you remove that pressure, it bounces back to being technical ceramic.
Wow, that's insane. It's actually funny you bring up dislocations, and I'll save the full thing for what did you research this week. But I was watching, MIT has a bunch of coursework online on YouTube for free.
Mm-hmm.
And they have a whole course on nuclear power, and they go into power plants and all of that, but also why radiation can embrittle materials and cause failures. And there was a whole part of that about it creating dislocations that then propagated and created cracks and all of that. So it's interesting to hear it come up multiple times within a week span of each other.
Yeah, I think about 4 semesters of my studies were just about dislocations, how they are created, how they move through materials. So for me, it's a very interesting thing. And the way you achieve this ductile cutting behavior while machining is actually by having a very negative rake angle on your tool. Because normally what your tool is doing, it's kind of like moving a spoon through ice cream. So your chip is in the chip flute of your tool, and you're tearing out the material. It's called shear formation of chips. And in that ductile behavior, the secret is your cutting depth has to be so small that your cutting edge is larger than the part you are cutting. And then immediately you have negative rake on your tool because, your cutting edge is standing over the material. And this gives tons of hydrostatic pressure on the material. The relevant question at that point would be, how do you achieve such a shallow cutting depth? We are talking about nanometers here. And how do you keep your tool from burning up? Because it's basically just rubbing. We are one step below rubbing. Your tool starts cutting, then it starts rubbing, and then if you go really, really down, you arrive at that ductile behavior. And I think the secret is a really, really well chosen cutting parameters, like choosing your spindle speed, your feed rate, your depth of cut. Everything just has to match. So I'm happy to talk about this here. It's not really a company secret, because if you don't own a Kern machine or similar precision, you won't ever achieve that cutting mode because your machine just won't be precise enough.
So how much guidance were you given from the cutting tool manufacturer versus how much did you have to develop?
It was actually, that project started because Kern has a contract manufacturing department. It's actually a whole plant devoted to contract manufacturing. And they got asked about quite a few ceramic parts, and they had no experience. So we set out in that project, and it landed on my desk, to just develop, let's call it a cookbook on how to machine ceramics. And I was very disappointed with my first trial. So I had all the tool manufacturers in Europe who are doing ceramics machining. I had them come over to Kern and had them show off their tooling. They arrived, they had tools with them, some even had material with them, and we started cutting it. And yes, it cut the ceramics, which is impressive in itself, but the results were really bad. You had edge breakouts and the tools failing after 1 hour. And I was a little bit disappointed. And then I set out in the way I usually do with my projects, and I defined some goals. And I said I want to be 50% quicker and 50% better than the best tool I've seen. This sounds crazy, but seriously, there's not been a lot of research done in ceramics milling, so it wasn't that out of space. And then I got frustrated because no matter what I didn't really improve on what the tool manufacturers were showing. And the reason is they are all machining in brittle mode. So their tool is made from diamond, it's very strong, and it can tear out a little bit of the material before it fails. But that's not really what I wanted to achieve. And then I had a very fun-filled weekend where I just went, you could call it batshit crazy on the machine. I did it on a weekend, so no one was there to see me light it on fire. And I'm not allowed to talk anything more about this because the German insurance companies will just throw me out if they hear anything. But it was a fun-filled weekend, and I destroyed many tools. And at the end, I discovered what makes a tool cut in a ductile cutting regime on a milling machine.
Well, that is pretty amazing, and that sounds like it was probably incredibly frustrating, but also a ton of fun by the end.
Yeah, I think the one moment I can tell you about is when I just tried going mad with the cutting speed and the tool was glowing white under the oil coolant. That was kind of like exciting.
Yeah, that sounds that's like welding on a gas tank when it's full of gas. You're like, well, this could
Yeah,
go
kind of.
it could go bad. We'll see.
Yes, exactly. That is what it was. It didn't go bad, so everything was fine.
Totally. Let's see, what else do we have? So Josh Hacko wrote in a bunch of questions. So let's kind
Yes.
of dive into some of those. For the Micro HD, what surprised you the most when testing the machine compared to the previous generations?
Oh, I have two fantastic examples for that. The first one is you have to imagine on my like lab code, I have a little pin that says I am not trained for this. And I'm seriously not trained for what I'm doing. So you will laugh now, but it's 4 years into my machining career in my second year at Kern that I had to touch off a part for the first time with like a tool and not a touch probe. I've never done that before. And the first time I did that was milling into the HD swivel axis of the very first HD because the laser kind of didn't fit. And they told me, like, Marvin, you're the only one from the apps department today. Can you make it a little bit wider? And I was like, no enclosure, no touch probe, no laser to measure the tool. So that was really scary. It's also up to date the most expensive part I have ever milled into. And what surprised me is the machine was so silent. I mean, it had no enclosure, and I turned on the spindle at like 20,000 RPM, and you could barely hear it. The reason is the hydrostatic guideways dampen so much. So all that ringing noise you normally have on a normal milling machine, that machine is like a factor or even an order of magnitude more silent. And that was like a wow moment for me. The second one was when I was preparing marketing material for the HD. So 15 years ago, Kern decided to drill through a human hair. They thought it would be a nice marketing gag. It's actually not that difficult, but they thought it would be a nice marketing gag, and this is something everybody can grasp. This is something I can tell my mother, like, we can drill through a hair, and then she's amazed, even though she knows nothing about CNC machines or what I do for work. And then I decided, okay, let's try it with the HD and mill into a human hair, but like engrave font onto it. And because the HD wasn't done yet when I had that idea, I had to try it out a little bit on one of our normal Varios. So they are the machines without hydrostatic guideways.
Mhm.
We still sell them, and they are like the medium model. So the HD is like the high end, and the medium Kern model is the Vario. And on that one, I tried it out, and it kind of worked. So I was able to get like a resemblance of font. But what is happening when you engrave into a hair is your machine has to move 10 microns one direction, then 10 microns back, and then forth. So you do a lot of really, really small movements. And if you do this on your milling machine, I don't advise you because you can seriously break something. After a couple of seconds, it will start making creaking noises. And that is because you have so much twist on ball screws normally, and everything is compensated digitally. So your control is like compensating the elastic deformation of your ball screws automatically. That when you're moving back and forth only a few microns, your machine does not like that. And you can actually wreck it in a couple of minutes.
Oh wow.
So don't try it home, kids. Don't try it home. And with the HD, I tried it out. And the thing is, when you're engraving a hair, you can't see it with the naked eye. So nothing is happening. Nothing. The machine is just moving there, and you have an end mill that is so small that you can't see it. And the action, you don't see anything. And even if you take it out and under a toolmaker microscope, you can barely see it. So I started trying to engrave the hair, and nothing. And then I did a second try, nothing. Then I looked at the tool, and the tool was somewhere, but not at the tool. Then I put in a new tool, and we're talking a 10 micron end mill there.
Oh my
And
goodness.
then I kind of found the hair. When I say found the hair, I found it in Z because you kind of can't touch proper hair. And the HD just engraved it. Like the first time I was at the correct cutting depth, I had a perfect engraving on the hair. And I know it doesn't make any sense to engrave a hair, but it was just like I was so blown away because beforehand it was just like the limits of the machine, everything was hurting the machine. And then it kind of was like, it just worked. And then we
Wow.
did another hair and it worked again. So it was kind of like, okay, this is crazy.
Wow, that's insane. So he also sent in some less than serious questions, but alongside of your experience and surprise with the HD, tell us the story of how you peer pressured an unnamed young Australian man into buying an HD.
Oh man. Yeah. Josh is actually a very good friend and they have a Pyramid Nano and I think they are kind of happy with it. It's an old machine, but it's still working and they are probably the most precise shop in the southern hemisphere. So that's kind of like, that's a big thing. But he was asking me about some parts, and sometimes my answers were helpful, and sometimes I was just being snippy, and I told him like, "Yeah, you have an old machine, just buy an HD." So I think the way I pressured an unarmed, much younger man is through showing him lots of attention and love, and then telling him buy a machine. I'm sadly running out of friends who want to buy HDs. So if you want to become friends and then buy an HD, I'm up for it.
But you heard it here first, guys. Reach out and buy an HD. Um, so another one of his questions was, in your time at Kern, what application or field is the most unique? Has there been any bizarre, non-conventional uses of the machine? I guess besides engraving.
I think the majority of the really bizarre things I'm not allowed to tell you about. I can tell you about a little bit of conjecture I had with our head of research and development last week. We were thinking an HD would actually make a perfect die stamping machine. I mean, it wouldn't be very fast and it would be super expensive and probably also wouldn't be very good, but it would be a lot of fun.
Okay, well, you're going to have to explain that a little bit more, for sure.
Yeah, I just crashed the HD on that day and kind of like smashed through the whole material. So
Oh, no.
yeah, we decided it would make a nice die stamping machine as well. We were both snickering at the end of our conversation. Nothing happened to the machine, so that was nice. No, I think unconventional uses of the Kern. For me, everything is kind of like conventional because it's just I get to hear about it every day. In general, I think it's not one bizarre thing that is happening, but the total of current customers. Because if you look at a week in our service department and the people that are calling, then like Monday morning, someone is calling who is grinding glass. And then 10 minutes later, someone is calling who is making microfluidic molds in nickel phosphorus. And then 10 minutes later, someone is calling who is roughing titanium parts. And then you think like, are they all doing it on the same machine and to the highest level of precision? And to me, this still blows my mind.
So nothing's bizarre because you live in the bizarre. That's a pretty amazing answer right there.
I'm afraid it is.
So his last serious question was: say somebody writes you a check for 10 million and asks you to set up a precision job shop. What support equipment and key equipment would you buy?
Yeah, I think the first machine I would buy is a Kern because I know how to operate them and they are actually awesome machines. And the second machine is probably measuring equipment because if you can't prove what you're doing, a Kern is kind of like, I wouldn't say wasted, but you kind of need to prove that you can do what the machine wants. And then I would get a lathe because I'm actually, and please never tell this anyone on the internet, but I think lathes are really cool. I mean, it's like John Saunders. He loves lathes as well. So I would buy a lathe and, okay, I'm smiling a little bit now. No, seriously, I would love to have a CNC lathe. Probably a very precise one, a Schaublin or maybe even one of the UPM diamond lathes. But just like, it looks so much easier compared to milling because you only have a couple of axes and no interrupted cut. So I would love to have a lathe. CMM wise, I'll probably go for a Zeiss CMM because I like them. I know how to operate them. And then I would get a white light interferometer. That's something I actually don't have at Kern. And they are made to have the highest resolution possible for analyzing surfaces. So my surface analyzing equipment at Kern, it kind of stops at 5 nanometers. And with a white light interferometer, you can actually go one order of magnitude below it. So I think my shop would have like one milling machine, one lathe, because I want to try it out, and the rest would just be stopped to the roof with measuring equipment.
Wow. So, speaking of diamond lathes, what is the Kern relationship with Inolite?
So Innolite is a German company, and they are good friends. They have a couple of Kern machines, and the Kern subsidiary for America, Kern Precision, is actually their machine dealer for North America. So
Oh,
they are not
okay.
our company, and in Germany we sometimes have phone calls talking about how to mill a material, or us asking them because they do their semi-finishing by milling on Kerns. Yes, semi-finishing by milling on Kerns. But we sometimes have phone calls, and we have I'd say, a pretty good and very open relationship. I sadly have never made it there. Our Dan DeMajor, he's IGS Dan on Instagram. He's currently at Innolite, and I'm very jealous.
So, right before I get into my next question, speaking of Dan, he asked, "Will you teach him all your secrets next week?" I guess he's coming to visit.
Yes, Dan is actually in Germany. The first time since the pandemic has happened, he managed to travel to Germany. And I'm actually on vacation next week,
Oh
but I've
no,
known Dan since my Datron days, and I arranged a day on one of our machines, which is super difficult. Normally, you have to wait like 6 months to get an open spot. But I arranged a day for him, and I'm coming in, and I think we will have a fun-filled day, and probably Instagram will get to see most of what we are doing.
that's awesome. So, jumping back real quick to Inolite, did you talk to them at all about diamond super finishing when you were doing your cube? Because I know that it's kind of a similar process what they're doing on their lathes, right?
Yeah, Uh, I think I might have asked them if I had the time.
Okay.
Like, usually, what Innolight and I, or at least the people I know at Innolight and I, are doing, we are trying not to wilder into everyone's territory. So they wouldn't ask me about micromilling, and I probably wouldn't ask them about diamond finishing. On that cube, I probably would have, just to one up Fanuc, but I didn't have the time. I started this project on a Friday afternoon. Like, everybody was already gone at Kern, and I just started it. So, and I had to finish it by Monday evening. So, yeah,
No
there was
time.
no
Yeah.
time.
No, that makes sense for sure. Let's see. Cyclos Garage asked, "Who supplies your MCD tooling, and is it possible for him to buy some?"
Well, obviously not from us, but I can tell you where we get diamond tools. So there's actually quite a few manufacturers for diamond tools. In the US, well, not the US, but Canada, and they ship to the US. The best one I know is K and Y Diamonds. They are actually one of the leadings worldwide. They are in my top 3. So for the US, go for K and Y. That's my personal opinion, but I think they are awesome. In Europe, you have quite a few more companies, and obviously, I know a lot more about the European companies. Everybody will tell you about Contour fine diamonds from the Netherlands. They are really nice diamond toolings, but quite expensive. A very good alternative, they are, I would say, in a similar quality, is from Switzerland, Dixie Poly Tools, which is
Hmm.
what, for example, Josh is using, Josh Hecko. And then from Germany, Matzdorf. That's Matzdorf, Matzdorf Diamond Tools. They are also an awesome supplier. But seriously, you can't really go wrong on diamond tools if you buy them from a reputable manufacturer.
Okay, great. And then you also have experience with 6C as well, right? I've seen you post quite a bit.
Yes, 6C is not MCD though. They do polycrystalline diamond tools. So 6C is definitely my go-to choice for ceramics or for milling carbide. But if you want to do mirror finishing, you need MCD, monocrystalline diamonds. So, and they don't have any, so they are out
Gotcha.
there.
Gotcha. That makes sense. Let's see. Oh, another interesting question. Cad Chris, another former guest of the show, asked, "A lot of great machines have small or big issues that people just learn to deal with. Does anything like this exist with such a high-end machine like a Kern? Chip evacuation, software updates, anything like that?" He doesn't want you to brand bash, obviously, but
Yeah. Okay. I think the biggest surprise here is that it's not only the machine. So chip evacuation on a Kern is not really an issue because the majority of customers don't make chips. And software updates, well, we've been building machines for quite a long time, and Heidenhain has been on the market for 30 years. It's a super stable control. So you don't really have a problem there as well. And tool changers, which used to be a huge issue for Kern, Josh can tell you about it. Well, we learned from our mistakes and we kind of overhauled the whole system. So if on a current micro series, any micro series, your tool changer has a problem, you hit emergency stop and start the machine again, and everything works again. It completely cleans every error up. So all of those small things, they don't really matter. I think what annoys people that have Kern machines is that it's not only the machine. I mean, you can buy a Kern and you can put it into a garage and you can start machining it. It's a damn fine machine, if I'm allowed to say that. But at the end, if you want to reach its full potential, it's not the machine, it's you. And that's actually what annoys me all the time because I'm not a very good machinist. So a lot of the time I'm struggling because it's me that it's bad and not the Kern.
Right. Well, and I think with any superlative machine or part of a machine tool, you think that like you're going to get this silver bullet and it's going to take care of anything. Like at my day job, we just got a bunch of RegoFix Power Grip.
Yes.
And you think like, oh, this is like the best tool holder system you can buy. But like there are things that they don't tell you that you don't think to ask. Like we never knew that you had to, or you're supposed to seat the tool all the way in the collet. So like if you're buying tools that they use shorter carbide on, all of a sudden your tool length isn't what you need it to be. And so you have to buy a short collet, or, tool's too long because it doesn't fit through the bottom of the collet. And like, that doesn't make it a bad system, but it is something that, you learn to deal with.
Exactly. And I think the biggest issue here on a Kern machine, to maybe do a little bit of brand bashing, is the power we put into the machine. That machine could be a lot better if we just put an air bearing spindle in it. I mean, we offer it, but seriously, this is an order of magnitude better if you get the air bearing spindle. Then again, if you have our normal spindle, it's an absolute beast, and the tolerance is enough for most everybody, even all the watchmakers. So yeah, this is nitpicking at a high level.
So before we get into the not so serious questions that people sent in, speaking of Kern power, talk to me about using ceramic end mills and your testing with those for aluminum.
Okay, so I have to say beforehand, I have very little knowledge about ceramic end mills. So they have been on the market for like years, and they are marketed as a non-wearing alternative to like carbide tools. And in that regard, well, just get a coated carbide tool. It's cheaper and it will hold as long as the ceramic tools for milling brass or aluminum. And a couple of months ago, they actually launched it 1.5 years ago, but I didn't hear about it, and Dylan, you probably didn't hear about BSQ Tech anyway, right?
No, not until you posted about them.
Yes, exactly. So they've been, before I posted, they had been on the market for over a year, but no one knew about them. What they did is they use a special kind of ceramics. It's not what you think it is, but I'm not allowed to say what it is, sorry. But what makes their end mills so crazy is that they are like super stiff. So they developed it for slotting, but you basically can't break that end mill. I've been running it at 30 meters per minute. I think that's 1,100 inches per minute in aluminum feed rate.
Holy
And
cow.
not at a light radial pass. It was like half the tool width in the material. And it survived. So that is like super crazy. At the same time, for that tool, you kind of need like a quick machine. So this is not something I would buy on a Tormach. This is something I would buy on a Matsura or on a Kern or a Hermle. So on a like quick moving, modern, stiff CNC machine. Otherwise, you're not going to enjoy it.
Okay. Yeah, that makes sense. I mean, yeah, I think that most machines couldn't accelerate enough to use those properly.
Exactly.
And then the other question I had is you've recently posted, I don't know, 4 or 5 videos of slow motion. Are you guys using the slow motion camera for speeds and feeds development, or is it marketing? Or, I mean, it seems like a little bit of both, but what spurred you guys to start going down that route?
Well, that camera is actually like all of the videos you see made by me with my hobby. So I bought that high-speed camera because I wanted a high-speed camera. No, I'm joking. It's my camera, so it's not one of Kern's. And I'm mostly looking at artifacts in milling. So something I'm presenting, I'm actually going to the US, Dylan. It's
You are?
crazy. Yeah, today my national interest exception arrived, so I'm allowed to go to the US now. And I'm traveling to the US at the beginning of November. I will be in San Francisco and I think Minneapolis. Yes.
Oh, cool.
And I'm helping one of our customers and then visiting a few potential customers with our salespeople. That's like the meh part. Now, our salespeople in America are nice. And I'm not saying unlike in Germany because they might listen to this, but yeah, you get the point. You have to publish this. Anyway, and then I'm going to the American Society for Precision Engineering annual meeting. And I'm holding a presentation on mirror finishing monocrystalline silicon. So the one you use for example, computer chips.
Oh, wow.
And there is a paper appearing as well for this. So I think at the end of November, it should be published. I'll put a link on my Instagram then. And it's also about ductile cutting regime, but this time not in a ceramic, but in a semiconductor. And I had an artifact appearing. So what I was doing is I was recording an acoustic emission spectrum on the machine while milling. Acoustic emission is kind of like holding a microphone to your part, but at the same time it isn't because you're not recording sound but vibration. But it's kind of like, think about this. It's what people in the 80s used to touch off grinding machines. You had a guy with headphones and a microphone sitting there and you could hear when the grinding wheel touches the part. And on that spectrum, so nowadays you're not listening, but you're looking at an oscilloscope at a very high frequency, 600,000 hertz is what my sensor goes up to. You can actually see every entry of the tooth individually because that resolution is just so high. And you have an amplitude and a tooth entry frequency. And I had a weird artifact that sometimes the amplitude on the tooth entry was larger and sometimes it disappeared. And I first looked for the error on the machine. So I started with the oscilloscope scoping channels on the machine, looking at the direct readout of our class scales, whether the machine is moving constantly or maybe stopping for a picosecond. Then I was looking at the spindle encoder, whether the spindle has like a variance in turning. And then I questioned whether I'm a very bad machinist and my stock on the material is always constant. And all of these turned out to not be the case. And then I took the high-speed camera and started filming it and managed to get some shots. I can upload them later on to show where you can see the chips flying away at like 20,000 frames. And I was very surprised to see that not every revolution of the tool netted a chip. Sometimes there was no chip coming. And then I overlaid that with the acoustic emission spectrum and it matched perfectly. So what is happening when you're jumping out of that ductile cutting regime and your tool is removing in a brittle way, that it's kind of like for one, maybe two revolutions, it's rubbing. So you have a very small amplitude on the acoustic emissions sensor.
Mhm.
And then the tool is kind of like cutting because there is enough material for it to cut because it didn't cut for two revolutions. So that's like a large amplitude. And then the amplitude disappears because the tool is not cutting anymore. And it was actually super cool to see on the video. And I probably would have never discovered this.
Wow, that's super cool. So is that sensor a piezo pickup that you attach
The
to the
acoustic
part?
one, yes,
Okay.
that's a piezo.
That's really cool. Yeah, and I love the video that you posted too of like showing what chip recutting looks like because I've always wondered
Yeah, that was cool.
how that happens when you're cutting on the outside of the part. Like you would always think like, oh, the chips just flow away, obviously, but watching the helix actually bring chips around and then feed them back into the cutter was really interesting.
Yeah, it was really cool. And I'm super happy, I have to say, that high-speed cameras are nowadays affordable. Like thinking back 10 years, I could have never afforded one. So that's pretty cool.
Yeah. Oh yeah. Yeah, it's making that kind of science a lot easier for even the home shop machinist to undertake if they wanted to.
Exactly. There's an awesome YouTube channel called Breaking Tabs who has some high-speed camera image of chatter on a home machine. That was fantastic. You have to check it out.
I actually watched that video. He was, I don't know if he's still part of it, but he was on the Instant Machinist Discord for a while, and he posted that video, and I could not believe, like, watching it bounce off of the material and then eventually break was super interesting to watch. I'll post a link in the show notes for this episode because it's definitely worth a watch.
Something I would love to see, but I don't know if it's possible. There is a computer approach. It's called Eulerian, like the mathematic Euler. Eulerian motion amplification. And what you can do is you take like a video of a machine or something, and it's looking at these sub-pixel contrast changes.
Yeah,
so like
yeah,
if you
yeah.
have and then it amplifies this, so you can actually see the movement in the video. And
Yeah, I was
normally
watching a YouTube video on that recently. They use it for like heavy machinery diagnosis. So like watching where
Exactly.
bolts are vibrating loose and things like that. It's insane.
Yeah, and I would love to have something like this with the high-speed camera, because actually the frequencies you can see are like the maximum frequency you can see is half your frame rate. So if you take it with your mobile phone, you can see up to 30 hertz. But on a high-speed camera, you could see up to 10,000 hertz. That would be really cool. But an issue is that Eulerian motion amplification, it only works on still objects. And I'm very unsure. We have a module for still objects at Kern, but it doesn't work if you have a rotating tool. So maybe a shout out to your listeners. If someone knows how to get it to work with a rotating tool, that would be really cool.
Oh yeah. Yeah, if anybody knows, please reach out to Marv because I want to see you do that. Like that, I think that would be so cool to be able to watch, active deflection in the tool and tool holder and part and all that stuff. So we had quite a few, we'll call them less than serious questions as well that I want to blow through. The Pragmatic Machinist asked, is Trixie Heist 2021 still on track? And assured me that you will know what this means.
Yes, I know. Well, the pragmatic machinist, I can tell you that Trixie is still very well loved and guarded, but Sam's second dog really is grating on his nerves. So I think even without a haste, we could cut a deal there.
Adam, Lady Machine Tech, asked, can he move to southern Germany so that he can do experimental CNC machining during the week and skiing in the Alps on the weekend? He said he'd be happy to be your lab assistant.
Well, skiing is much nicer during the week, and machining is much nicer on the weekend because then you actually get machine time. So it's a firm no.
Josh asked, when are you moving to Australia?
Josh has been trying to convince me to move to Australia, and he thinks it's going to be like a golden solution, me working for him. I don't think he has realized that I have no idea about machining, and I'm bored if I have to do more than one part of a single thing. So chances are it's never happening.
His next question was, who's your favorite watchmaker?
Oh, that's easy. It's IWC. No, it's obviously Josh. He's a darling.
And it says, what does it feel like to be mainly on Instagram and not working?
I told him to never mention that. There was a fun conversation I had with our CEO at lunch this week. I was being very cheeky, like very cheeky. And then he told our other CEO that they should give me another warning. And I started laughing. And then the first one said that the folder with my warnings is already overflowing. So I think they will not care.
And then John Split 141 asked, if you had another choice of a country to work in besides Germany, what would it be?
Oh, that one is actually easy. It would probably be Switzerland because they have awesome precision industry as well and mountains. And one thing that is never happening is me moving to a warm country without mountains. So Australia is so out.
Yeah, I mean, you do live in an insanely beautiful country. Like I remember after we met at AU, you had sent me I was going back through our Instagram messages and you sent me a picture that you're like, oh, I'm home. And like looking at it, it is like the most idealistic picture that we all think of when we think of, the Swiss Alps or, any of that kind of stuff, like the most beautiful mountains you could possibly imagine. So I understand not wanting to really move from there.
Yeah, I'm very lucky to be able to live here. It's cool.
So that brings us on to shop news and new things segment. So what is new in your world? Is there anything you're currently working on that you can share, both personal or at work? What's new in your world?
Well, I already shared about the silicon milling, which will appear on Instagram in the next couple of weeks. I shared about my America trip, so those are like the two biggest ones. I have a paper coming out in probably 2 to 3 months about ductile cutting of silicon carbide, so the ceramics.
Okay.
That's going to be interesting. For us at Kern, we are getting a second HD to our application department. We were running out of machine time a lot, so that was like super nice. And yeah, the high speed camera, I think you will see a lot more videos in the coming weeks on that one.
I'm excited about that. Yeah, even just watching the five you posted so far, it's really cool getting to see that kind of nitty gritty of the cut that you never get to see when you're just machining parts.
Yeah, what something I haven't tried yet is like doing high speed milling. So obviously the steel milling was kind of like slow RPM on the spindle. I think 8,000. I'm excited to see what it looks like when you really turn up the spindle and get cracking on the material. That's gonna be cool. Maybe on Sunday if there's bad weather.
Yeah,
Oh,
I
and
mean,
emo is coming up. I forgot. So
oh
new in
yeah,
the next weeks, trade show. I'm going to a trade show again. I'm so excited. It was like before COVID and the pandemic arrived, I was like, oh, I'm never going to another trade show. It's such a hassle. And now, with nearly 2 years without trade shows, I'm so excited to go to emo.
and
So
that's
if
in
anyone
Italy.
is coming, yes, it's in Milano this year, Italy. And it's really cool because it's only every 6 years in Italy. So I'm really excited, never made it there before. So if anyone is coming to emo, I think we are in Hall 12, booth C62. Don't don't nail me down on this one, but I will be there from Wednesday to Saturday. So if you are coming by, say hello.
That's fantastic. I wish you all the luck and all the fun. I mean, I know I was talking to quite a few people this week because this should have been the week, I think, of IMTS last year or this year. And so we were all kind of lamenting that we missed the trade shows.
Yeah, yeah, definitely. It cured me of my dislike of them, so it's high time they start up again.
Definitely. Well, that brings me to the last question I ask every guest, which is, what did you research this week? And it can be literally anything. We've had people talk about baby stuff, cooking, what's been popping up in whatever search browser you use.
Okay, okay, fully putting down the nerd here. This week I spent a lot of time on how you call different pronunciations in the German language. Yes. Okay, so for example, if you make in German the noise, it's called stimmloser veraler Frikativ, and that marks German as the most complicated language ever.
Yeah, that's
So
quite the
that's
name for such a
something,
small sound.
yeah, so that's something besides machining related that I researched this week. Machining related, I can also share. I've been writing very busily on my paper this week, and I've researched the influence of lubrication on ductile cutting regime. Not a lot of research there, but this is something I looked for a lot.
Oh, so I guess I never asked you that. Well, when we were talking about that, I had assumed when you were ductile cutting ceramics that it was all dry,
No, it actually isn't. If you do it dry, your tool will just burn up instantly.
and you don't get
So,
any. What's the word I'm looking for? Like I know a lot of people cut steels dry and things like that because you don't want thermal shock to the cutting edge. You
mhm.
don't get any of that when you're ductile cutting ceramics.
So I think if you would, for example, use diamond coated tools, this would be a problem. But diamond actually has a massive heat conductivity. It's used nowadays as a heat conductivity layer in super high energy electronics already. And because the material is pretty uniform, you don't have a coating and something with different thermal expansion. Okay, wait, I have to start up why people don't do it in steel. So the problem is not really the thermoshock in steel, but the problem is that the coating on your steel tool has a different thermal expansion coefficient than it has in the carbide below it. So when the coolant hits your steel tool, what is happening? Obviously it's shrinking down from the thermoshock, and because the coating is shrinking at a different rate, it splits off. And if you have for example, a carbide tool, it will just burn away in steel because it gets so hot that it doesn't work anymore. And with ductile cutting in ceramics, you're kind of like your feeds and speeds and everything is so aggressive. I'm not allowed to tell you what it is exactly, but if I told you, your eyes would probably pop out at what I'm doing there. And if you don't cool, or actually if you don't lubricate, because your tool is rubbing so much, it would just burn up. I know this because I have a bit of video footage when it's dry, and it takes like half a second, and then it's smoking already.
Oh, wow.
So, not really smoking, and then it's glowing, and then it's gone. So you can't really do it dry. It kind of works with minimum quantity lubrication, and it works very nicely with cutting oil and okay-ish with emulsion.
Okay.
Yes.
That's interesting. Yeah, it's great to hear that explanation of why people cut dry with carbide tools and steel. Then I never thought about the coatings having a different thermal expansion than the carbide underneath, but that totally makes sense.
There's actually some research being done on making cutting tools from binderless carbide. So usually your carbide, it's tungsten carbide, so tungsten and carbon, and that is also a ceramic. And because you can't sinter particles large enough, what they do is they make like nanograin particles, very, very small ones, and then they use either a nickel or a cobalt-based metal binder. So your carbide tools are actually a compound material, metal and ceramics. And that is one of the reasons why you can't sharpen them indefinitely, because once you go with an edge sharpness below that carbide grain, well, there's nothing to sharpen. And there is binderless carbide. You can't really make huge chunks from it, so making like a whole end mill is difficult because you need intense pressures. But that one is actually temperature resistant up to twice of what carbide is. So carbide gets soft around 600 degrees. Soft in the way of it's not as hard as before, you can't bend it. And binderless carbide you can actually heat to over 1000 degrees Celsius before it gets soft. So there is a lot of research being done into making steel cutting tools from that.
Really? So that would be like a screw-on head type end mill or something like that, since they have
I
to be
think that is
smaller.
what they are, I think that is what they are doing at the moment, yes.
Wow, that's really interesting. I had no idea that you could make binderless carbide. That's amazing.
You can also make binderless cubic boron nitride, Sumitomo.
Hmm.
They are well known in, I think, like turning inserts. They have turning inserts made from binderless carbide, and have super long lifetime in turning, and they actually leave a spectacular finish.
Well, like you said, I would imagine you can sharpen them
Yes,
much more than a carbide insert, so that makes sense.
exactly.
Wow, I'll have to look into that because that sounds very interesting. I mean, I don't think that any of my customer parts have any application for that, but just as the machining nerd I am, I want to look into it.
Mhm.
So before we wrap up, is there anything that I did not ask that you wanted to talk about or that you thought I should have asked about?
We could have a marketing segment about Kern machines. No, I'm joking. I've talked enough about them already. No, I think it was really nice. It was a pleasure talking to you, Dylan.
Yeah, likewise. Thank you so much. And real quick, wrapping up, new Patreon thank yous. Thank you to Tom, Inspiration Metalworks. Thank you for joining and being a past guest. And Simon Teague, thank you for joining the Patreon. Appreciate it. All of your guys' support helps me organize interviews like this and have amazing people like Marv on. So again, thank you so much for taking the time, Marv. I appreciate it. I've learned so much. I usually have to go back and listen to these episodes after editing anyway, but now I'm going to go back through and like make a bunch of notes because I've got so many things to research this week. So I really appreciate it.
Thank you for having me.
And thanks everyone for listening. We'll be back next week.